Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on chapter 6. Now we've made it to the second objective, and the focus of the second objective is Le Chatelier's principle. Now this principle states that if a stress is applied to a system in equilibrium, the system will adjust to counteract that stress and re-establish equilibrium. And this principle, it can be applied to changes in concentration, pressure, volume, and temperature. So we're going to go over each of these variables and how changes made are counteracted by the reaction to re-establish equilibrium. We're going to first start off with discussing concentration. Now, I'm going to write an example reaction and we're going to reference it as we go through our different points. The reaction is nitrogen gas reacts with 3 moles of hydrogen gas to give us 2 moles of ammonia gas. Now, the first point that we want to make is what happens if we were to add more reactant. Let's say that we go ahead and we add more nitrogen gas. What happens? Well, when reactants are added, the reaction quotient Q becomes less than the equilibrium constant K. And then the system will shift in the forward direction to produce more products, thereby increasing Q until it equals K. So the main point here is if you were to add more reactants, if more nitrogen gas, for example, is added, the system will shift to the right to produce more ammonia. It will favor the formation of product. So that is what happens when you add more reactant. All right, what about if you add more product? What happens then? Let's go ahead and say that we instead add more ammonia, all right, more product. Well, when you add more product, Q becomes greater than K, and the system is going to shift in the reverse direction to produce more reactants, thereby decreasing Q until it equals K. So again, for the reaction, if more ammonia is added, the system will shift to the left to produce more nitrogen and hydrogen gas. So it is going to favor the formation of reactant. Now that intuitively should make sense. If we have more reactant, how do we reestablish equilibrium? By forming more product. If we add more product, how do we reestablish equilibrium? By forming more reactants. Now here's another scenario, another 2 scenarios that we're going to cover. What if we went ahead and started to remove things? All right. What if we removed reactant? All right. Let's say that we were removing nitrogen gas from our reaction. What would happen? How would the system reestablish equilibrium? Well, if we're removing reactants, Q is going to be larger than K. All right. The system will actually shift towards the reactant side. It will shift in a way to produce more reactant to compensate for the removal of reactants. And the system is going to shift to the reactant. So if we remove reactant, we're going to favor the formation of more reactants to reestablish equilibrium. And you guessed it, the same principle applies if we decide to remove product. If we were to remove ammonia, the system will shift towards the products. It will attempt to produce more products to reestablish equilibrium. And in this case, when product is removed, Q becomes less than K, all right? And the system will shift in the forward direction to produce more products, thereby increasing Q until it equals K. So in short, if we remove product, we favor the formation of more product to reestablish equilibrium. So those are the 4 important points to keep in mind in relation to concentration. So I'm going to say it one more time. If we add reactant, we're going to favor the formation of product to reestablish equilibrium. If we add product, we're going to favor the formation of reactant to reestablish equilibrium. If we start removing reactant, we're going to favor the formation of more reactants to reestablish equilibrium. And if we remove product, we're going to favor the formation of products to reestablish equilibrium. So those are our main points for concentration. Now, the next thing that we want to talk about is pressure. And when we talk about pressure, we could actually simultaneously talk about volume. So we're going to talk about pressure changes and volume changes and what the consequences are in terms of making those changes and how the system reestablishes equilibrium. Now, changes in pressure and volume, they affect gaseous equilibria. The system is going to shift to counteract the pressure change by changing the number of moles. So again, let's use our same reaction, nitrogen gas plus 3 moles of hydrogen gas give us 2 moles of ammonia gas. And let's start with our first scenario. Our first scenario is let's increase pressure, all right, or decrease volume. So you can increase pressure by decreasing volume. So these 2 points go together. What happens? When we increase pressure, decrease volume, the system is going to shift in the direction that produces fewer moles of gas so that it can decrease the pressure and reestablish equilibrium. So for example, if we're looking at our reaction here, when we increase the pressure, we're going to shift the equilibrium to the right, because in that direction, we produce fewer moles of gas. In the reactant side, we have 4 moles of gas total. On the product side, we have 2 moles of gas. So when we increase pressure, decrease volume, the system will shift in the direction of fewer moles of gas. So here in our reaction, that means for our specific reaction, fewer number of gas moles means that we're going to form more product here. That's not always the case. This is a reaction by reaction basis. But when you increase pressure, decrease volume, your system will shift in the direction that produces fewer moles of gas. Okay, now the second scenario is what if we decrease pressure or increase volume? When you decrease pressure, increase volume, the system is going to shift in the direction that produces more moles of gas, thereby increasing the pressure to reestablish equilibrium. So for our reaction, we said that the reactant side has a total of 4 moles and our product side has a total of 2 moles. When we decrease pressure, increase volume, we favor the side that produces more moles of gas, so we favor the side of the reactants. Our equilibrium is to the left. It will shift towards the reactants. Now, an important note here is that these changes are only applicable to reactions involving gases. Solids and liquids are essentially incompressible, so their concentrations do not change with pressure or volume changes. So this works out for us because our reaction is just gas species. So that's our point on pressure and volume. Now, our last variable that we want to talk about, and I think that this is a really fun one, is temperature. So changes in temperature affect the equilibrium constant K itself because temperature is related to the reaction's enthalpy change. And we're actually going to have 2 main categories here. We're going to have what happens to temperature when temperature changes for endothermic reactions and what happens when we change temperature for exothermic reactions. There's a different set of rules depending on whether it's endothermic or exothermic. Let's start with endothermic. An endothermic reaction has a delta H that is greater than 0. So that means heat is absorbed in these reactions. So heat can be considered a reactant. So let's write an example reaction. Let's write dinitrogen tetroxide, all right, reacts to give us 2 moles of nitrogen dioxide. So this is our example reaction. This reaction is endothermic. Now, if it's endothermic, remember, heat is considered a reactant. So sometimes to help you remember that, I would just write heat on the reactant side, just so I can not mess this up. Okay, so for an endothermic reaction, what happens if we increase temperature? When we increase the temperature for an endothermic reaction, you can think of this as we're adding heat. All right, adding heat is going to shift the equilibrium to the right. Right? When we increase temperature, we're adding heat. So think of this like we're adding reactant. If we're adding more reactant, what happens? Our reaction favors the formation of products to reestablish equilibrium. All right? So that's why it's so important to write heat when you're working through these problems. Remember, for an endothermic reaction, heat is part of the reactants. And if you write it down, then you'll easily work through this. Increasing temperature means we're increasing quote unquote heat, which means we're increasing our reactant. What happens when we increase reactant? We favor the formation of product. Now, what happens if we decrease temperature? If we're decreasing temperature, then that's like we're removing heat. That's like we're removing reactant. If we're removing reactant to reestablish equilibrium, we want to form more reactant. So our reaction favors the formation of more reactant. So that is for endothermic reactions. Again, let me repeat. For endothermic reactions, heat is considered a reactant. When you increase temperature, you increase heat, which means you're increasing the amount of reactant. Thereby, your reaction favors the formation of product to reestablish equilibrium. What happens when you decrease temperature for an endothermic reaction? It's like you're removing heat. So it's like you're removing reactant, and so your reaction favors the formation of more reactant to reestablish equilibrium. Okay, what about exothermic reaction? So I'm going to write an example exothermic reaction right here. 2 sulfur dioxide gas plus oxygen gas gives us 2 SO3 gas. Okay, now for exothermic reactions, delta H is less than 0. That means heat is released in these reactions, so heat can be considered a product. So we're going to go ahead and write it in the product side just so we keep things clear. Now, our first scenario for exothermic reactions is what happens if we increase temperature. If we increase temperature for an exothermic reaction, that means that we're adding more product, right? We're adding more heat, and that means we're adding more product for an exothermic reaction. To reestablish equilibrium, it's going to favor the formation of reactants. So that's for increasing temperature. What about if we decrease temperature for an exothermic reaction? If we're decreasing temperature for an exothermic reaction, we're removing heat, which means we're removing product. And so our reaction is going to favor the formation of more product to reestablish equilibrium. So again, let me summarize this once more. For an exothermic reaction, heat is considered a product. When you increase temperature, you're adding more heat, thereby adding more product. And so your reaction is going to favor the formation of reactants to reestablish equilibrium. If you decrease temperature for an exothermic reaction, that means you're removing heat, that means you're removing product, and so your reaction is going to favor the formation of more product to reestablish equilibrium. So those are all our main points for Le Chatelier's principle. And here, This diagram kind of summarizes all those points. So let's go over it one more time for good measure. We talked about concentration changes. The system shifts to counteract the change, moving away from added species or towards removed species. Then we talked about pressure and volume changes. The system shifts to produce fewer moles of gas when pressure increases or volume decreases, and it shifts to produce more moles of gas when pressure decreases and volume increases. And then finally, we talked about temperature. For endothermic reactions, increasing temperature favors products, while decreasing temperature favors reactants. For exothermic reactions, increasing temperature favors reactants, while decreasing temperature favors products. Understanding these principles really allows us to predict how a system at equilibrium will respond to various stresses. So it provides a really powerful tool for controlling chemical reactions. With that, we can actually go ahead and move into our last and final objective. Our third objective is titled Kinetic and Thermodynamic Control. In a chemical reaction, products can often be classified as either kinetic or thermodynamic, and understanding the differences between these products and the conditions that favor their formation is really important in predicting and controlling the outcomes of reactions. Let's first start by covering kinetic products. The kinetic product is the product that forms the fastest. It is favored under conditions that limit the reaction's ability to reach equilibrium. Now, those conditions are lower temperatures and shorter reaction times. They will favor the kinetic product. And these conditions favor the formation of the kinetic product because it forms through the pathway with lower activation energy, even though it might not be the most stable. Then there's also the thermodynamic product. The thermodynamic product is the most stable product, and it is favored under conditions that allow the reaction to reach equilibrium. Those conditions are higher temperatures and longer reaction times. With sufficient heat, the reactants, they can overcome a higher activation energy barrier to form the thermodynamic product, which exists at a lower overall energy state and is more stable. Now, a reaction coordinate diagram is a graphical representation that shows the energy of a system as a reaction progresses from reactants to products. The height of the hills or peaks on this diagram represents the activation energy required to reach the transition state from the reactants or from the products. So here you see this diagram. In terms of kinetic pathway versus thermodynamic pathway, the kinetic pathway is associated with lower overall activation energy peak. All right, it's associated with the lower activation peak on the diagram, and it leads to the formation of kinetic products. This is because the kinetic product is going to form faster due to the lower energy barrier that needs to be overcome. But something that you'll notice is that the kinetic product is higher in energy than the thermodynamic product. The thermodynamic pathway is associated with a product that exists at this lower overall energy, despite potentially having higher activation energy peaks on the diagram. This is the thermodynamic product. It is more stable. Now, in biochemical systems, these principles of kinetic and thermodynamic control are very relevant. Many biochemical reactions are regulated to favor either the kinetic or thermodynamic product based on the organism's needs. So for instance, metabolic reactions, they often involve ATP. This is a high energy molecule. The breakdown of ATP is a thermodynamically favorable process, but it's controlled kinetically by enzymes in the body to ensure that it only happens when it's needed. In enzyme activity, factors like temperature and solvents can really alter the balance between kinetics and thermodynamics. So, for example, higher temperatures can provide the necessary activation energy to overcome barriers and reach a more stable thermodynamic product. However, enzymes, being proteins, they can denature at high temperatures, thereby favoring the kinetic product. And so there's a balance here. In summary, whether a reaction follows a kinetic or thermodynamic pathway depends on the reaction conditions, and understanding this, again, can provide insights into the control and regulation of biochemical reactions. And with that, we've completed all the topics that we need for Chapter 6. I really hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Feel free to email me if you want to talk about something. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.